So in the last few presentations, we had discussion on the basic circuit element inductor. Now in this presentation, we will be talking about the series combination of resistors or resistors in series. So in the video lecture of a basic circuit element resistor, we already discussed that what is a resistor. A resistor is basically a component which is used to oppose the current in the circuit or which provide opposition to the current in the circuit. So in this presentation, we will be discussing the series combination of resistors. So basically, what is a series combination of resistors? Resistors are said to be in series if there exists one and only one connection between the adjoining resistors. So if we connect two or more resistors in a manner that there is nothing connected between the adjoining points of these two resistors or three resistors. So for that, let's take an example in which we have two resistors are connected in series manner between point A and B. These two resistors R1 and R2 are in a series because there is nothing connected between the adjoining points of these two resistors. Now if we connect another resistor in the adjoining point of these two resistors, then so now we cannot say that these two resistors R1 and R2 are in a series manner because there is another resistor connected between the adjoining point of these two resistors. Now to understand the series combination of resistors in a more brief way, let's take an example in which we have a battery source is connected in series with three resistors R1, R2 and R3, and there is current I flowing in this circuit. So for series combination, there exists only one path for the current. So the current through this series combination of resistor will be the same. So for series combination, the current through the series network is the same through every points. If there is a current I flowing through this battery or this voltage source, then the same current would be through this point, and the same current would be through this point, and the same current is flowing from this point. So for a series combination, the current is the same at every point in the circuit, and the voltage is divided across the terminals of each resistor. So the larger is the resistance value, the larger would be the voltage drop across the resistor. And the polarity of the voltage drop across the terminals of each resistor would be determined by the flow of this conventional current from the positive terminal of the battery towards the negative terminal of the battery. And as we discussed in the video of electrical power, that the current is entering at the positive side of a resistor and leaving the negative side of a resistor. For each resistor, the current is entering at the positive side and leaving the negative side of this resistor. So the voltage drop across this resistor 1 is, let's say, V1, and the voltage drop across resistor 2 is, let's say, V2, and the voltage drop across the resistor 3 is, let's say, V3. So according to the law of conservation of energy, the voltage supplied by this source is equals to the voltage absorbed by these three resistors. So the voltage across the terminals of this battery is E, and the voltage drop across R1 is V1 plus V2 plus the voltage drop across R3 is V3. Now according to Ohm's law, E is equals to I, which is the current through this battery, into RT, and this RT is basically the equivalent resistance of this circuit or this network. So by putting this equation here in this equation, so we get I into RT, and the same current is flowing through this R1 and R2 and R3. So according to Ohm's law, V1 would be equals to I into R1 plus this V2 will be equals to I, the same current through this resistor 2 and R2 plus I into R3. So I RT is equals to, so I is common in this side, so by taking I common, so we get R1 plus R2 plus R3. So I will cancel I. So the resulting equation becomes RT is equals to R1 plus R2 plus R3. And this RT is basically the equivalent resistance of the series combination of a network. So RT represents the equivalent resistance of this series network. And for any series combination, the equivalent resistance is equals to the sum of all the resistors connected in series. Now from this discussion, the series combination of resistor, we derive the following characteristics of a series combinations of resistors, in which the first one is, for the series combination of a resistor, same current flows through all parts of the circuits. So we already discussed this, the same current is flowing through each point of the series network. Now according to the second point, different resistors has their individual voltage drops. So higher the resistor, higher will be the voltage drop across the resistor, lower will be the resistor, lower would be the voltage drop across the resistors. According to the third point, the voltage drop across each resistor in a series combinations are additive. So by additive term we mean that which satisfies all the laws of additions, which are commutative law of addition, commutative law, associative law, and all others law of additions. Now for a series combination of resistors, applied voltage would be equals to the sum of a different voltage drop across each resistors. So we have already discussed that according to the law of conservation of energy, the voltage supplied by this voltage source would be equals to the voltage drop in this network. Now for series combination of resistor, resistances are additive. So like a voltage drop is also additive, the resistances are also additive. Resistances satisfies all the laws of addition, which are commutative law, associative law, and all the others law of additions. And powers are also additive. So we will be discussing the power in the series combination in the upcoming presentation. Now to understand this discussion in a more brief way, let's take an example in which we have a DC voltage source which is connected in series with the three resistors R1, R2 and R3. So the voltage of this DC voltage source is 30 volt and the resistance of the first resistor is 3 kilo ohms and the resistance of this second resistance is 4 kilo ohm and the resistance of this third resistor is 6 kilo ohm. And we are asked to find out the current through this series network and the voltage drop across each resistor in this network. So first of all, we need to find out the equivalent resistance of this network. So the equivalent resistance for a series combination of resistor is equals to R1 plus R2 plus R3. So R1 is 3 kilo ohms plus R2 is 4 kilo ohms plus R3 is 6 kilo ohms. So the equivalent resistance of this network is equals to 13 kilo ohms. And the voltage across this DC voltage source is 30 volts. Now according to Ohm's law, E is equals to I into RT. So we are asked to find out the current through this series combination of network. So the current would be equals to E divided by RT. And we know that E is equals to 30 volts divided by RT is given, which is 13 kilo ohms. So the resulting current in this series network is equals to 2.3 milliampere. So 2.3 milliampere of current is flowing in this network. Now the voltage drop across each resistor is, now for the resistor R1, let's say the voltage drop is V1, which is equals to I, the same current flowing in the series network, into R1. So I in this case is 2.3 milliampere, while R1 is 3 kilo ohms. So the resulting voltage drop across V1 is equals to 6.9 volts. Now the voltage drop across the second resistor is, let's say, V2 is equals to I, the same current through R2 into R2. So we get I in this case is 2.3 milliampere, while R2 is 4 kilo ohms. So V2 in this case is equals to 9.2 volts. Now the voltage drop across the third resistance is, let's say, V3 equals to I into R3. So V3 is equals to I in this case is 2.3 milliampere, while R3 is 6 kilo ohms. So the resulting voltage drop across the third resistor is 13.8 volts. Now we already discussed that the voltage supplied by this DC voltage source is equals to the sum of all the voltage drop across each resistor. So let's say Vt is the total voltage drop across the network, which is equals to V1 plus V2 plus V3. So the total voltage drop in this network is equals to V1 is 6.9 plus V2 is 9.2, while V3 is 13.8. So the resulting voltage drop is equals to 29.9 volts, which is approximately equals to 30 volts. So it is proved that the voltage supplied by this DC voltage source is equals to the sum of voltage drop across each resistor in this circuit. And we already discussed that for a higher resistance the voltage drop is high, so the third resistance is a higher value or the higher rating, so the voltage drop across the third resistance is high, which is 13.8 volts. So for lower resistance value the voltage drop would be lower, which is 6.9 volts. So it's all for today's presentation. If you have any doubt, ask in the comment section. See you in the next one.